Hello friends, this is Chetan from GT Networks. Today let us discuss about two-dimensional random variable. Let x and y be two random variables defined on the sample space S, and if a function x comma y that assigns a point in R square, so then that is called as two-dimensional random variable. So this xy should assign a point in R square. R square is nothing but this real line, real space, two-dimensional minus infinity. So this is x-axis, positive x-axis, and positive y-axis, negative x-axis, and here it is negative y-axis. So this is R square. So if x comma y assigns a value in this space or in this plane, that is called as two-dimensional random variable. And let us look at the joint mass function. So that is given by p of x comma y, that is x takes the value xi and y takes the value yi. So that is equal to, provided that x equal to xi comma y equal to yi, and we know that the sum of the probability is 1. So that is double summation of xy over the range of x comma y. So that is equal to 1. Okay, and the marginal density is given by, this is marginal density, that is if you want the marginal density of x, then you should take the summation over j, that is summation over yi. So that is pi, and similarly if you want the marginal distribution or the marginal probabilities of y, then take the summation over x. Okay, and the conditional probability function is given by this expression, probability of x given y, that is equal to probability of x equal to x comma y equal to y, that is probability of x intersection y, and then probability of y. So it is as good as probability of a given b, that is equal to probability of a intersection b divided by probability of b, provided this probability of b is not equal to 0. So the same condition is here, and if you want y given x, again this in the denominator will change, that is probability of x equal to x instead of y equal to y, and this condition should be met. And the distribution function is given by f of xy. So in one dimensional random variable, if x is a random variable, then f of x, that is probability of x less than or equal to x. So this is the distribution function. In case of two-dimensional random variable, that is f of x comma y, we have this condition, that is x is less than or equal to x and y is less than or equal to y. Suppose this is a real plane, and then this is a value, that is it is x and this is y. So x comma y, then probability of x less than or equal to x comma y less than or equal to y. So this is x line and this is y line. So x less than or equal to x means this space, y less than or equal to y means this space. So this is the distribution function for two-dimensional random variable. So for one variable or one-dimensional random variable, it is, suppose this is x, so this is x less than or x means this entire this probability, here it is a space or a plane. Okay, and let us look at a few properties, that is probability of a1 less than or equal to a1 less than x less than or equal to b1, and a2 less than y less than or equal to b2. So that is given by f of xy comma this the upper limits, that is b1 b2 b1 comma b2, plus and the lower limits a1 comma a2 minus this b1 b2 and sorry, it is b1 b2 a1 b2 a1 and b1 a2. Okay, and this a1 a2 b1 b2 belongs to R, that is real line, and f of minus infinity of y equals f of x of minus infinity, that is equal to 0. See here, so this is minus infinity, this is plus infinity in y axis, and here it is plus infinity, it is minus infinity. So x comma minus infinity, suppose this is x, point x, comma minus infinity means this point here minus infinity. so this would be 0, and minus infinity comma y, so this is minus infinity comma y may be any point, suppose it is here, so this value is also 0. Okay, and f of infinity comma infinity, that is this is infinity and this is infinity, this, so f of infinity comma infinity is 1, and these points takes the 0 value. Okay, and if you double differentiate that f with respect to, that is partial differentiation of f with respect to x and y gives the probability mass function or density function. And now we'll look at the joint density functions. So f of x comma y, so it is a joint density of x and y, so that could be given by the partial differentiation of x with respect to f and y with respect to f, so that is dou square by dou x dou y f of xy. So that can be given as limit as delta x and delta y tends to 0, probability of x lying between x and delta x plus delta x, and y lies between y and y plus delta y. So and this delta y tends to 0, fine, divided by delta x and delta y. So this is nothing but f of xy. Okay, and similarly as in case of discrete mass functions, here you have that the marginal density is given by, you have to integrate, there you used to sum over x to get p of y equal to p of xy, and to get p of x, sum over y p of xy. Here instead of sum in continuous distribution, what you have integration. Okay, so here I am integrating over the range of y, so this is the range of y, so it may be minus infinity to plus infinity, or 0 to infinity, or 0 to 1, or any other values which belongs to real line. So that is the over the range of y, and we should integrate the joint density function with respect to y to get the marginal density of x. Okay, so in case of discrete it is summation, fine. And similarly what is f of y, so f y of y, this can be given by minus infinity to plus infinity f of xy, and you want to get y, so you should integrate with respect to x. Okay, so over the range of x you should integrate, fine. And similarly the conditional density function is given by this expression, and f of x given y, so x given y, so this could be given by f of xy divided by f of y. Okay, fine. And suppose if x and y are independent, then the density function f of xy, so this could be written as like this, it is product of f of x and f of y. Suppose I have let me give a small example here. Suppose f of xy equal to theta e power minus theta x into theta e power minus theta y. Okay, so this is nothing but theta e power minus theta x plus y, so this is f of xy. Okay, so this can be written as f of x into f of y. Okay, so since f of x y, this joint density can be written as product of the individual densities, so this is independent. What is independent? X and y are independently distributed. Okay, and let us look at a few more examples and properties regarding this distribution function, density function, random variables, and other concepts in upcoming videos. So thank you friends, thank you for watching my video. Have a nice day.